Hello one and all, welcome to another online video by Einstein Academy. In this video, we'll be looking at learning outcomes I from the topic of atomic structure from the JCH2 chemistry syllabus. Learning outcome I states that candidates should be able to explain the factors influencing the ionization energies of elements. So the first thing to understand this learning outcome is to define what ionization energies are. So we define ionization energy as the amount of energy required to remove one electron from each atom or ion in a mole of gaseous atoms or ions, producing 1 mole of gaseous cations. This is a pretty handful of words, and everything will become clearer when we use the chemical equation to define this ionization energy in the next slide. Moreover, the removal of the first electron from an atom is termed as the first ionization energy, while the removal of the second electron from a cation of 1+ charge is termed the second ionization energy, so on and so forth. We can have third ionization energy, fourth ionization energy, etc., etc. So in a chemical equation, we remove 1 mole of electron from each gaseous sodium atom to form 1 mole of Na+ gaseous cation, and this definition is known as the ionization energy. Notice that in the definition, it includes the word gaseous, and hence it's extremely important to include the state symbols in this chemical equation that defines ionization energy. The first ionization energy of sodium atom is plus 496 kilojoules per mole. So one thing that I would like to discuss here first is that it's a positive value. And the reason that it's a positive value is that because the electron is attracted to the positive charge of the nucleus, hence we actually have to supply energy in order to remove the electron from the attraction of the nucleus. Hence it's positive, which is endothermic, and energy is required to do ionization energies. The first ionization energy of magnesium is to remove 1 mole of electron from 1 mole of gaseous magnesium atom to form 1 mole of Mg+ gaseous cation. And the first IE of magnesium is plus 738 kilojoules per mole. Again, it's a positive value. On the other hand, the second ionization energy of magnesium is the energy required to remove 1 mole of electron from 1 mole of Mg+ gaseous cation. And in doing so, we will form 1 mole of Mg2+ gaseous cation. Again, the second ionization energy of Mg is positive, and the value is plus 1451 kilojoules per mole. So the second point to discuss here is that the second ionization energy is actually larger than the first ionization energy, and we would like to understand why. If you look at the number of protons and number of electrons for the magnesium gaseous atom, we would know that it actually has a total of 12 protons, and 12 electrons. Okay? Whereas for the Mg+ cation, because it has already lost an electron, so the number of protons still remains as 12 because there is no change in the number of protons when it became a positive cation, whereas the number of electrons is now 11. Okay? In this case, 12 electrons is attracted to 12 protons of the magnesium atom, while in this case, 11 electrons is attracted to 12 protons of the Mg+ cation. And since there is a smaller number of electrons attracted to the same number of unchanged positive charges in the nucleus, the attraction felt by the remaining electrons will be stronger for the successive increasing positively charged cations, and hence successive ionization energies is always larger than the previous one. So the second IE is larger than the first IE, and the third IE will be expected to be higher than the second ionization energy. So to summarize what I've said, ionization energies are usually positive values because energy is required to overcome the electrostatic forces of attraction between the nucleus and the electron to be removed. Moreover, successive ionization energies increase because the remaining number of electrons decreases, but they are now more strongly attracted to the same number of positive charge in the nucleus. Okay, so now having defined ionization energies, we are ready to look at the factors that influences ionization energies. How do we apply this? For example, if we want to compare the ionization energy of atom A to atom B, then we need to understand what are the factors that will result in the difference in the values of the ionization energies between the two atoms. And these are the three factors that influences the ionization energies. Factor 1 is the size of the positive nuclear charge. Factor 2 is the atomic and ionic radius, while factor 3 is the screening effect. Remember when we talk about the electrostatic forces of attraction, if we have a 2 plus charge and a 1 minus charge, the electrostatic forces of attraction between these two charges is larger than a 1 plus charge and a minus charge. And hence, if the nucleus actually has more protons, the attraction between the nucleus and the valence electron will actually be stronger. And hence, as the size of the positive nuclear charge increases, the outermost electron will be more strongly attracted to the nucleus. And if this is true, more energy will be required to remove the electron in the ionization process. And hence, it can be said that if the number of protons increases, it would result in a stronger attraction of outermost electron, which would result in an increase in the ionization energy because more energy is required to overcome this stronger attraction. So this is factor 1. Factor 2 is atomic and ionic radius. We also mentioned that if we have a plus charge and a minus charge, the attraction between this will be stronger as compared to the same charges but further separated. So if the charges are more further separated, the attraction between the opposite charges will be weaker. Now, as the atomic radius increases, the distance between the nucleus and the valence electron, this distance is larger. As the distance increases between the nucleus and the valence electron, the attraction will be weaker, and hence, as atomic and ionic radius increases, the outermost electrons will be less strongly attracted to the nucleus, and consequently, less energy will be required to remove it. So, as radius increases, attraction decreases, and IE will consequently also decrease. This is factor 2. For factor 3 is screening effect. So let's compare between the lithium ion. For the lithium ion, there are 3 electrons. And the idea of the screening effect is the following. The nucleus is attracting the valence electron through the attraction between the protons and the electron. However, there is an inner shell electron that is acting like a shield that basically blocks the attraction of the nucleus and the valence electron, and hence the word screening effect. The inner shell electron is actually screening the positive charge of the nucleus from the valence electron. Consequently, let's say we go to another element, which is sodium. And sodium has 3 shells. And the innermost electrons are shielding the nucleus from this valence electron. For this case, there is a total of 10 innermost electrons. Whereas for this case, there is only 2 innermost electrons that is shielding the nucleus from the valence electron. And hence, in this case, the sodium will have a higher screening effect. And if the screening effect is higher, the attraction between the nucleus and the valence electron will be weaker, and this will result in a decrease in the ionization energy. So, the outermost electron is shielded from the attraction of the nucleus by the inner electrons, and it's only the number of innermost electrons that matters. The greater the number of inner shell electrons, the greater the screening effect, and the less strongly the outermost electron is attracted to the nucleus. Consequently, less energy is required to remove it. So logically, if screening effect goes up, okay, so what causes this? Basically an increase in innermost electrons. This will result in a decrease in attraction, which would then result in a decrease in ionization energy. So this is the way to think about screening effect. And this is factor 3. And these 3 factors influences ionization energy, which we would then summarize with the term using effective nuclear charge. The meaning of the word effective nuclear charge is how effective nucleus is in attracting electrons. Okay, so it's used to describe the effective attraction between the nucleus and the outermost electron, having taken into consideration of the 3 factors that influences ionization energies. And if the nucleus is more effective in affecting the electron, the ionization will be greater, vice versa. So we'll talk about more on how to use this as we discuss further on. This is a graph showing the ionization energy as a function of the atomic number, basically of the different elements. And we would like to note 2 things from this graph. Notice that in period 2, the ionization energy generally increases from lithium all the way to neon. And the ionization energy also generally increases from sodium to argon, with 2 anomalies. Notice that the ionization energy of boron is lower than that of beryllium, and the ionization energy of oxygen is lower than that of nitrogen. And in period 3, the ionization energy of the group 3 aluminum is lower than that of the group 2 magnesium, whereas the ionization energy of sulfur is lower than that of the ionization energy of phosphorus. Okay, so these are 2 anomalies. But in general, the ionization energy increases across a period. The second thing that we can note is that down a group, as you go from beryllium to magnesium, the ionization energy decreases. When you go from lithium to sodium, it actually decreases slightly. When you go from carbon to silicon, it decreases. When you go from nitrogen to phosphorus, it decreases. When you go from oxygen to sulfur, it decreases. When you go from fluorine to chlorine, it decreases. So basically, ionization energy generally increases across a period, but decreases down a group. And we would like to understand why by applying what we learned, the 3 factors that influences ionization energies. Across the period, the number of protons increases, so this will result in an increase in the effective nuclear charge, because the nucleus will be attracting the valence electrons more strongly. However, the screening effect remains relatively constant because our electrons are added to the same subshell as the outermost electron. Let's compare between lithium and nitrogen. So lithium has 2 electrons in the first shell and 1 electron on the outermost shell. Whereas for nitrogen, even though it has much more electrons than lithium, the electrons are added to the outer shell. So nitrogen has a total of 5 valence electrons, but in both cases, there are only 2 innermost electrons, which are the only thing that matters when it comes to screening effect. As such, the screening effect is the same for both atoms. Okay, so this one has no difference to effective nuclear charge. And the overall conclusion between these 2 factors is that there is an overall increase in the effective nuclear charge. So across the period, effective nuclear charge generally increases, and hence the ionization energy increases because the electrons is more tightly attracted to the nucleus. So again, the general trend is ionization energy increases across a period. As mentioned previously, there are 2 anomalies. The ionization energy of boron is lower than that of beryllium, and the ionization energy of oxygen is lower than that of nitrogen. In discussing all ionization energy problems, the first step to do is always to first write out the electronic configuration of the species that we are trying to remove electron from. The electronic configuration of beryllium is 1s2, 2s2, whereas for boron is 1s2, 2s2, and 2p1. Notice that the removal of the first electron from beryllium involves the removal of a 1s electron. On the other hand, the removal of the first outermost electron from boron involves the removal of a 2p electron. And because the 2p is on average further away from the nucleus, than the 2s electron, the 2p electron actually experiences smaller attraction from the nucleus, and hence it's actually easier to remove the 2p electron as compared to the 2s electron. That's the reason why the ionization energy of boron is lower than the ionization energy of beryllium. For the oxygen, same thing, we have to write out the electronic configuration of nitrogen. So for nitrogen, it's 1s2, 2s2, 2p3, whereas for oxygen, it's 1s2, 2s2, 2p4. If we were to write out the electronic configuration in this manner, we would see that the removal of an electron from oxygen involves the removal of a paired electron, whereas for nitrogen, it would look like this. It would involve the removal of an unpaired electron. Remember when we first studied how do we fill up electronic configuration, we mentioned that we would like to put electrons singly in each orbital before we pair them up. The reason is that electrons that are paired in the same orbital are on average closer to one another and experiences greater interelectronic repulsion, which actually destabilizes the electron. So when we remove an electron from the oxygen atom, we are removing an electron that is paired, that is less stable because of the fact there's greater interelectronic repulsion, and hence we actually require less energy to remove the first electron of oxygen as compared to that of nitrogen. So this explains the second anomaly of why the ionization energy of oxygen is lower than that of nitrogen. In words, boron has a lower ionization energy than beryllium, even though it has one more proton. The reason being, the first IE of boron involves the removal of a 2p electron, which is further away from the nucleus and better shielded than the 2s electron of beryllium. As such, it is less strongly attracted to the nucleus and less energy is required to remove it as compared to the 2s electron of beryllium. The second anomaly, oxygen has a lower ionization energy than nitrogen, even though it has one more proton, because the first IE of oxygen involves the removal of a 2p electron that is paired. The paired electron experiences greater repulsion than the unpaired 2p electron of nitrogen and is less stable. As such, less energy is required to remove it as compared to the unpaired 2p electron of nitrogen. So this explains the two anomalies in the general trend of increasing ionization energies across a period. Now we are ready to discuss the last part, the variation of ionization energy down a group. When we go down a group, the number of protons increases. So this will result in an increase in effective nuclear charge. However, let's say we compare between lithium and sodium. For lithium, it has only two innermost electrons that is shielding the valence electrons from the nucleus. So two innermost electrons. As compared to sodium, sodium actually has a total of 8 more electrons that is shielding the valence electrons from the nucleus. This has a total of 10 innermost electrons. So in this case, this shielding effect will be stronger in sodium as compared to lithium. And hence, generally, when you go down a group, the screening effect will actually increase due to the increase in the number of electron shells, and this will result in a decrease in the effective nuclear charge. Moreover, when you go down the group, the distance between the nucleus and the valence electron also increases, and this will result in a decrease in the effective nuclear charge. Summarizing these three factors, with one factor increasing the effective nuclear charge and two factors decreasing the effective nuclear charge, the overall effect is that the effective nuclear charge decreases down a group. And consequently, we can see from this chart or this graph that the ionization energy actually decreases down a group. This is for group 2, and this is for group 1. Hopefully that this lecture has summed up and explained to you the factors influencing the ionization energies of elements and how do we use it. In the next lecture, we'll go through the final learning outcomes for this topic, and then we will go through the past year A-level questions that basically test on understanding ionization energies. Hope you like this video. If you like this video, just hit the like and subscribe button. And I'll see you for another episode for the online lecture by Einstein Academy. Thanks for tuning in and see you.